Okay, so we're doing two sections today, which I was going to split it up, but they pretty much said we're not supposed to give any homework over the break, so we're going to get these two sections in and we won't have any homework on Tuesday. There won't be anything coming out of Tuesday. So rational functions. Remember, the word rational means fractions. Okay, fractions. So now we're dealing with functions that are fractions. We kind of did a little bit of that when we were dividing in the function operations. We divided. So f of x equals, and you've got a polynomial in the numerator and a polynomial in the denominator. Notice that the q of x, which is the denominator, it says does not equal 0. Again, that stops us from dividing by 0, which we're not allowed to do. The p of x and the q of x are polynomials. And you know what you do with polynomials? You factor. Yeah, these are functions. Generally, what do you do with functions? You graph. And expressions you simplify, or you do operations with them. Equations you solve. So we're going to do this as our only treatment of the graphing functions is today. And then we get into the adding, subtracting, multiplying, and dividing, the things like you copied, if you copied the, and then we solve equations is the last lesson. So examples of rational functions, that are in that format that we just saw on the previous slide. Right, the top three are all like one polynomial divided by another. The two that are not good examples, you could say that x is x over 1, couldn't that be a rational function? I mean, it's already a polynomial, so we don't need another category of function for it. I mean, we're really most interested when we've got variables in the denominator. That's what turns it into the rational function. Okay, the next one is this g of x, a rational function. It absolutely is a rational function, but it's not written in that format of p of x divided by q of x. It's actually two terms. I mean, we could write it in that format. I could multiply the first one by x over x, and then I would have x to the third plus 1 over x. Okay, now it's written as one function divided by another. But some of the rules that we're going to deal with here, they don't really apply unless it's written like one function divided by another function. Okay. So the graphs of rational functions, except for the first one we're going to do, this is the 8.2, have irregular graphs that can't be transformed like we've done. So mostly what we're going to do, we're not going to try to graph those functions. We are going to do the inverse variations, but we're not going to graph the others. But we will study their characteristics. And you'll see what that's about in a minute. And you can graph them. I imagine that next year, go to math analysis, you will graph the rational functions. I mean, you'll go we're going to take like 4 or 5 steps along the way. There may be like 1 or 2 left to go, and you can do that, if they have you do that. Right, so the rational functions, the main thing about them is they can have both horizontal and vertical asymptotes. So again, another reason why you got to get straight on the y, what is y equals and which one is x equals, because it doesn't go away. Okay. So the first one, okay, again, this is 8.2, an inverse variation. Do you remember doing inverse variations in Algebra 1? I mean, you did 2 kinds of variations. You did direct variation and inverse variation, right? Remember, direct variation was the y equals k times x. It's linear. Graph would go through the origin because the y-intercept is 0. Now, we're going to do that stuff. It's section 8.1 in the book, but we're going to do that after this test. That's the last thing we'll do right before the exam. because it really doesn't, it's kind of its own little subject. We have to do direct and inverse and then a new one called joint variations, and all those questions are kind of a type like z varies jointly as x and y. If x equals this and y equals that and z equals that, then find z when x equals this. I mean, just its own kind of question that you get. Okay, so y equals k over x. Again, this comma, x does not equal 0, that's a domain statement. They're telling us can't divide by 0, and we know that. Right? The k is a constant. It's not a variable. Right? It will be filled in by a number when we get going, but it could be any number. It's called the constant of variation. Okay. So just to see what it looks like, I graphed y equals 1 over x. So I let k equal 1. And I made my table of values here. I did from 1 to 4, and then I threw in 1/2, and -1 to -4. Those are all the values. And you could see I've drawn in 2 asymptotes, and then the graph itself has 2 branches. Right? There's both of those green lines. One of them is in quadrant 1, and one of them is in quadrant 3. There are 2 branches. You know, one of the things, the SOLs have been rewritten again, and we don't have to deal with them this year. Next year, we're supposed to teach to the new standards while we continue to teach to the old standards, even though the test itself won't actually include the new standards. And then the year after, then everything's the new standard. But one of the things they're going to talk about is the difference between a continuous and a non-continuous function. This is an example of a non-continuous function, because in order to draw it, you would have to like pick up your pencil and then move your pencil to another part of the graph. It's not just like one continuous line like a polynomial. So this is discontinuous. Okay, so why does it have the asymptotes? Well, first of all, it says x does not equal 0. Okay, so that's why it has to have an asymptote at x equals 0. Right, that's why it's got that dashed red line right there. Okay, now, why does it have an asymptote on the x-axis? Y equals 0. Well, 1 over x is a fraction. How is it that you make a fraction equal 0? You have a 0 in the numerator. Okay, but this can't have a 0 in the numerator. It's already got a 1. So there's no way to make the fraction equal 0 because you can't make 0 over anything because it doesn't have a place for that. It's already got a constant. So there's no way for the graph to touch the x-axis or the y-axis, so it's got asymptotes. And we're going to label them. Y equals 0, x equals 0. The domain, you know, these graphs go infinitely close to those 2 lines, so the domain is x does not equal 0. The only value of x which is not included is that one number. All the other values of x are fine. And same thing for the range. Y does not equal 0, but it has every other value. So that's what you want to look at and say, okay, that's the parent function. That's what the parent function of an inverse variation looks like. Okay, now we can compare. Okay, well, what would be the difference if I change the constant? Right? And of course, it's going to change the graph a little, but it doesn't really change it significantly, not for what we're interested in here. So I'm comparing here 1 over x and 2 over x. And, you know, the green line is 1 over x. The blue line is 2 over x. They both have the same pattern, right? You got one branch in quadrant 1, one branch in quadrant 3. It still has an asymptote on the x-axis and an asymptote on the y-axis. The domain and the range are the same. You know, yes, one's a little further out from the axes, but for our purposes, for our sketching purposes, they're about the same. So if we change what's in the numerator, it doesn't change for us the sketch of our graphs. You know, if we want to be more accurate, we could plot some points, but we won't do that. Okay. Good. Good, Joby? You okay? Okay, now let's see what happens if we put a minus in front of the function. Okay, what usually happens when we put a minus in front of a function? It flips the graph, right? So the blue line is the negative 1 over x. And you can see that the branch that used to be in the first quadrant, now it's in the fourth quadrant. Right? The branch that used to be in the third quadrant is now in the second quadrant. Okay, so this is how you graph an inverse variation, right? It says include and label the asymptotes. But the truth is you start with the asymptotes. The asymptotes aren't just telling you like where the graph can't cross. They're giving you guides to where you're supposed to draw the graph, because the graph will approach those asymptotes. So let's see what all's going on in this function, okay? What about this minus in front? So it's going to be flipped. What about a plus 2 inside the function? Left. Right. What about a minus 1 after the function? Down. Right. So I'm going to draw my asymptote. So left 2, so that's going to be about right there. And down 1, that's going to be about right there. And then I'm going to label them, because I always said to label them. X equals negative 2. Y equals negative 1. Okay, because it's been flipped, which 2 quadrants am I going to draw this in?
2 and 4.
2 and 4, okay? Now, when you're doing this, you're not talking about the quadrants from before. We're talking about use the asymptotes to define the quadrants. So in quadrant 2, it's going to be like this. In quadrant 4, it'll be like this. And that's all we're looking for. Just make sure that you do show it approaching the asymptote. Like sometimes students will draw it and then they just kind of instinctively draw across along the x-axis here. And that'd be wrong, right? Because it's supposed to be approaching the asymptote. Okay, what is the domain and the range? What is the one value of x this graph won't have? Negative 2. X does not equal negative 2. Range. Y does not equal negative 1. Okay, it'll have all the other values of x and y, but it won't have those two. That's it. I'm going to just throw this in too, because we're going to talk about this anyways. But so we've talked about end behavior before. We talked about end behavior with polynomials, where it always meant like as x approaches plus or minus infinity, the graph either went to positive or negative infinity. But when a graph approaches a horizontal asymptote, that's also end behavior, right? As x approaches positive infinity or negative infinity, it looks like the graph is going to approach negative 1. Whatever is the value of the asymptote, that's what it's approaching. Now, we saw one other function that had an end behavior. What was that? That had a horizontal asymptote, let's say. You just took a test on it. Say again? Which one had the horizontal asymptote? The exponential did. So, you know, an exponential has a horizontal asymptote. At least on the one side, it's approaching the horizontal asymptote. Okay. Okay, so try this one. Okay, so there's only one shift going on, right? What is it? Down 5, okay? And so that should be moving the 1, 2, 3, 4, 5 horizontal asymptote. That's good. Okay, so what about the vertical asymptote? Where is it? If you didn't go left and right, it's still at 0, right? So just draw that in. And then label x equals 0, y equals -5. Okay, which two quadrants have I got to draw it in? 1 and 3, right? It's not flipped, right? That's a positive. So we're going to draw it here. And what is the domain in the range? X does not equal 0. Y does not equal -5. Okay, I think you got another one. Try that one. So where should I draw the vertical asymptote? +3. X equals 3, right? Make sure you use the variable. Where should I draw the horizontal asymptote? +2. Okay, so label x equals y equals 2, x equals 3. Which two quadrants? 1 and 3. Domain and range. Domain x does not equal 3. Y does not equal 2. Okay. So that's section 8.2. Okay, now we're going to do 8.3. Right, we're not going to graph, but we should be able to find zeros, horizontal asymptotes, vertical asymptotes, domain, and end behavior. What do we mean by the zeros of a function again? Say again? Yeah, x-intercepts, right? They're the values of the x values that make the function equal 0. I had brought this up before. Let's see if I still got it up here. I hate it when it does that. These are kind of examples of graphs of rational functions. And you could see, see the two green lines there? Those are the vertical asymptotes. It looks like there's also a horizontal asymptote there, right? Doesn't look like there's any zeros. Let's see what another one looks like. Okay, that looks like the inverse variation. Another inverse, it looks like it's been flipped. Ooh, kind of tilted a little bit. Oh, we could. There's another one. That doesn't even look like it has a vertical asymptote. Looks like it's got a horizontal asymptote. Oh, there's a different one. See, the shapes are all different. They're not going to just be one fixed shape, and that's why we're not going to graph them. We're mostly just interested in things we can transform. Okay. So I'm going to leave that one in the background because I want to go back to that one later. Okay, so let's see how we work this out. So given a rational function, this is going to be like 4 slides in a row. They're going to tell you how to find zeros, vertical asymptotes, domain, horizontal asymptotes, and end behaviors. That's 5 slides. Actually, it might be 6 slides, but 5 things. So the zeros of the function are the zeros of the numerator. Again, if you make the numerator of a fraction equal 0, the whole fraction equals 0. Okay, that's why. So the zeros of the function are the zeros of the numerator. Okay, here's the next one. The vertical asymptotes of the function are x equals the zeros of the denominator. Right? You got to have the x equals in front of it, because that's how you make a vertical line. Good. Okay. Right. The domain of the function is x does not equal the zeros of the denominator. Okay. Okay. Now, for horizontal asymptotes, there's actually 3 rules, right? And the rules depend on the degrees of the numerator and the denominator. Do you remember, what do we mean by the degree of a function? The highest power of x, right? So if the first rule is here, right? Number 1. If the degree of p, which is the numerator, is less than the degree of q, which is the denominator, then you have an asymptote at y equals 0. And we kind of did this one, right? The example is y equals 1 over x. And it did have a horizontal asymptote at y equals 0. So that's what happens whenever the denominator has a higher power of x than the numerator. Okay, if the numerator, p, has a higher degree than the denominator, there is no horizontal asymptote. You know, like x squared over x. I mean, we could simplify that. That's just plain old x. That's actually the identity function. And, you know, it's not if it's a horizontal asymptote, then you expect that your function is approaching that line as it goes towards the ends of the graph. And obviously y equals x, it's not. It's just going towards positive infinity on one side and negative infinity on the other. So that's rule 2. So which is the case that's not included on this slide? Equal, right? We've got the degree of the numerator is less. We've got the degree of the numerator is more. But we don't have what happens if they're equal. And if they're equal, then, you know, if I write the p of x and q of x like we did in the chapter on polynomials, standard form, highest degree term on the left, right? If the highest power says x to the n and x to the m, if the n equals m, they have the same degree, then the horizontal asymptote is y equals the ratio of the leading coefficients. Y equals a over b. And we'll do a few examples, you'll see how that looks. Okay, let me do one more. Okay, the end behavior of the graph. As x approaches plus or minus infinity, if there is a horizontal asymptote, then y approaches the horizontal asymptote. I don't even know why I have it like in that format there. I want to take that off. Just say y approaches a over b. Now let me go back to this graph to point something out. So you look at those green lines, and they are the asymptotes, right? There's two vertical asymptotes, and there's the one horizontal asymptote. But this shows perfectly that there's a difference between a vertical and a horizontal asymptote, besides the fact that one's vertical and one's horizontal. Vertical asymptotes, the graph can never touch, ever, right? Horizontal asymptotes are the value that the function approaches. It's the end behavior. That's what it is. In fact, look at this graph right here. It's crossing the horizontal asymptote, but it's doing so when x values are small. The horizontal asymptote is telling you this is what it'll approach when the x values get big, right? It's okay to cross the horizontal asymptote when x values are small, but vertical asymptotes you never touch, can never, they're not in the domain. So that's the basic difference between the two. Okay, back to our movie. So identify the zeros, vertical asymptotes, horizontal asymptote, domain, and end behavior. So one at a time. Zeros. So what did we say about the zeros? How do you find the zeros? Read the rules. The zeros of the function are zeros of the numerator. Okay, well in this case, what are the zeros of the numerator? None. 5 is a constant. It's never going to equal 0. So none. Okay, vertical asymptotes. I'm going to abbreviate here. Vertical asymptotes. And actually, there can be more than one, so I'm going to say with an S. Okay, this is where you're going to have to get into either factoring or in some way you're going to have to find the zeros. How do we factor x squared minus 1? Here's the difference of squares. X plus 1, x minus 1. It's a factoring pattern that is assumed to have been mastered by now, because it's going to be all over the place in this chapter. And every time it's there, it's going to be expected that you factor it, and that it's not actually a challenge. It's just kind of like, okay, just so we can put a little bit of a factoring problem in there. Okay, so now what are the zeros of this denominator? -1 and 1. So we have to say that the vertical asymptotes are x equals 1 and x equals -1. Okay, what is the domain? Look back in the rules. What did it say? Literally, word for word, what did it say? Okay, so x does not equal 1. X does not equal -1. Okay. Okay, horizontal asymptote. right? We got to know which one of those three rules are we going to use. Is it numerator higher degree, denominator higher degree, or is it the same degree? Garrison? Which has got the highest degree? The denominator has the higher degree, so what is the horizontal asymptote? Y equals 0. Okay, and then the last one, end behavior. As x approaches plus or minus infinity, y approaches what? Yeah, the horizontal asymptote. Those two always match. Right, just like these two always match. Yeah, one is x equals, the other one is x does not equal. Now, the only thing that we haven't done is actually graph the function. And if you were going to graph the function, first you'd put your asymptotes on the graph, and then you would have to make a table of values. And usually the directions will say something like, include 1 point in between all the zeros and vertical asymptotes, and 1 point on either side which is beyond the furthest zero or vertical asymptote. And then just with that, just kind of sketch in the graphs. But we're not going to do that part. Maybe you'll do it next year. I don't know how they do this. I mean, one thing, if you tried, let's say, if you try to graph things like that in your calculator, sometimes they don't work. You got to go. Okay. Your calculator has a hard time with vertical asymptotes. Just like when the logarithm, you know how it would like stop the graph at a certain point? Sometimes it'll draw like this odd line on the graph. It makes it look like it's part of the function, but it's actually just the calculator having trouble. So sometimes your hand-drawn graphs of rational functions are better than the calculator can come up with. Now you got a new calculator. I haven't seen how this one might do it, but okay. I think I got another one for me to do. Okay, so let's do this one together, and then the next one will be for you. So zeros. Zeros of the function. X equals -1, right? It's the zeros of the numerator. Okay? Vertical asymptotes. Okay, so we need to set the denominator equal to 0. And what are we going to find? Right? Which is non-real, so it can't be on your graph. So there are no zeros in the denominator. So you say none. Well, if there's no vertical asymptotes, then what's the domain? All real numbers, right? There's no restricted values, so it's all real numbers. Okay, horizontal asymptote. Okay, which of the rules are we going to use again? Number 1, degree of the numerator is less than denominator. Number 2, degree of the numerator is more. Or number 3, they're the same. One and 2, still that first rule, y equals 0. So the end behavior, EB, as x approaches plus or minus infinity, y approaches 0. Okay, so here's a you try for you as soon as you're done. Done. Okay. So try that one. What did you say about the zeros? None. Right? If you try to solve x squared plus 9 equals 0, you get x squared equals negative 9, imaginary. Right? So there's none. Remember? Just like on the last slide, we did that with the denominator. X squared plus 9 equals 0 means x squared equals negative 9. Right? So that's going to give us non-real solutions. And when we graph, everything's real numbers. So that can't be on there. Okay, vertical asymptotes. Okay, well, you had to factor this, right? This is x minus 5 times x plus 3. So what are the vertical asymptotes? X equals 5, x equals negative 3. Right, what does that make the domain? X does not equal 5. Right? X does not equal negative 3. Okay, horizontal asymptote. Let me abbreviate that. Okay, which of the rules are we going to use this time? They're equal this time, right? It's x squared in the numerator, x squared in the denominator, so it should be y equals the ratio of the leading coefficients. 1 over 1, which is 1. Okay, and what does that make the end behavior? As x approaches plus or minus infinity, y approaches 1. Okay. So let's see. Notice like when I do the vertical asymptotes, I put an s at the end because you can get more than one. Why wouldn't I do the same thing with horizontal asymptote? You know, could a graph be approaching two different horizontal lines and still be a function? You know, that would, you know, if I had another horizontal line there that the graph was approaching, then it wouldn't be a function anymore. So you're never going to get more than one horizontal asymptote. You can get more than one vertical asymptote. Sounds like a good test question, though. Okay. Okay, try that one. What did you say were the zeros? Negative 5 and 12. I got to factor the numerator. Okay, the vertical asymptote is negative x equals negative 3. Domain is x does not equal negative 3. Horizontal asymptote, none, because the numerator has a higher degree than the denominator. Now, for end behavior, I'm just going to say NA. I mean, the truth is it's not going to be approaching a fixed horizontal line. It's going to be going off towards positive or negative infinity. And, you know, we know sometimes that is our end behavior with polynomials, but they would never ask you that in the context of a rational function. Right? With a rational function, it's either going to be, it'll be a horizontal asymptote, y equals whatever that is. Okay, now there's just one more I'm going to show you, and then we're done. Okay, identify zeros, etc. So, numerator. I've got to find the zeros of the numerator. Can I factor x to the third plus 27? What kind of factoring pattern is it? Does 27 sound like a familiar kind of number? It's a cube, right? So it's x to the third plus 3 to the third. This is the sum of cubes. So we had a formula for this. Right? This is x plus 3 times x squared minus 3x plus 9. Okay, and denominator, a common factor of x, so it's x times x plus 3. Okay, zeros. Okay, so the zeros are the zeros of the numerator. So what's 1 0? -3. Again, remember when we did this before, I told you, the only solutions you're ever going to get out of that trinomial are imaginary. So that's going to be the only real zero will come from that first factor. So we don't have to worry about the last one. The vertical asymptotes. X equals 0, -3, right? The zeros are the denominator. Okay, domain. X does not equal 0 or -3. Horizontal asymptote. X to the third over x squared means none. Rule 3, none. And so the end behavior is NA, not applicable. Okay, now that's not exactly right. What I just did there is not exactly right. And this is the difference, and this textbook doesn't actually ask you any questions like this, but you'll get asked it next year for sure. If you notice our two zeros, right, 0 and -3, one of them is coming from a factor which actually is in common to the numerator and denominator, so it would cancel. That means that this is not going to be a vertical asymptote. Remember, a vertical asymptote, besides being a dashed line in your graph, the graph of the function is approaching it. It's going towards infinity or -infinity as it gets that close. Okay, and if you look at the graph, and that is the graph of that function, at -3, it's clearly not doing that, right? This is what it's doing at 0. It's going off towards infinity on both sides. But at -3, it appears to just go right on going. Now, the truth is, there's a hole in the graph. Right at x equals -3, there's a gap. You can't see it. If you did it in the calculator, you wouldn't see it on the graph. But if you went to the table of values and went to -3, it would say error, right? Because you can't divide by with x equals -3. That's called a hole in the graph. It's not a vertical asymptote. It's called a hole in the graph. So normally the way you do that is you say for these are both called points of discontinuity. The 0 is a vertical asymptote, but the -3 is called a hole. X equals -3. And then I can take it off of here. There's still restrictions to the domain. Domain is still x does not equal 0, x does not equal -3. But you don't expect the graph to veer off towards infinity or -infinity if it's actually, taken from a common factor of the numerator and denominator. This book doesn't have any issues like that. The books I've taught out of in the past, first they would have you find the points of discontinuity, and then they would have you classify them into one or the other. This is a hole, this is a vertical asymptote. I guess they know what they're doing. And that's that. And that's the homework. So on the first page, which is the inverse variations, include and label the asymptotes, state the domain and the range. On the second page, these are all problems that say graph, but you don't have to graph. Just do what we did in class for all those problems.